Yes. No, after the introduction to construction materials, the first material is this. Welcome to lecture 12 of modern construction materials. Today we start talking about specific materials that we use in construction, and we are going to begin this module with steel and other metals. On this picture here you have an interesting structure. This is not the Eiffel Tower of Paris, but a half scale replica of the Eiffel Tower in Las Vegas, and Las Vegas has a lot of structures which are interesting, and lot of them are metallic structures. And the other metal, of course, that is used a lot in Las Vegas is money, and they use a lot of coins in the slot machines and the casinos. Metals have been used since a very long time by human beings. Copper, lead, iron have been used by people for thousands of years, and it is said that one of the greatest achievements of mankind is the discovery of how to smelt ore to obtain metals, that is, how to get metals from the natural state of ore. Copper is believed to have been used since about 6000 BCE. Then the Bronze Age began about 5000 years ago, and bronze started being used instead of stone for making tools. Bronze, as you know, is an alloy of copper, tin and other elements, and it is very useful since it is strong, hard, malleable and does not corrode very fast. Iron has been used since 4000 BCE, and we can say that the Iron Age even continues today with the widespread usage of iron and steel, and today we will see why iron and steel are so popular as construction materials and why they continue to be used. It is said that high quality steel was produced in South India perhaps as early as 3000 BCE. Most metals are found in nature as ores, oxides, sulfides, carbonates, and though the extraction of the metal from the ore is based on simple chemistry, the problem is to do it on a large scale, on the industrial scale. Another problem with the usage of metals is that the metal tends to revert to its original state by corroding, that is, it becomes an oxide or tends to become an oxide. Therefore, in metallurgy the two important goals are how to extract the ore in an economical manner and how to maintain the metal without corroding, and the product of this is what we use in civil engineering applications. This is a brief introduction to how metals are formed, common processing methods. We have the melt, the molten metal, and this can be cast as an ingot, as a bulk piece of metal that can be worked on, shaped later, or it can be put directly into the shape that we want through sand casting where the mold is of sand, or some other material, or investment casting where we use a disposable mold. This is also called lost wax casting and so on, where we use a die or a cast which is destroyed during the casting. Then the ingots can be worked and shaped through rolling, forging, extrusion, drawing. We will see this in more detail in a minute, and then there is a lot of finishing involved in terms of machining and joining of the different elements. For forming, we use different processes related to hot working. The hot working processes depend on the plasticity, which is higher at higher temperatures, and this is done above the recrystallization temperature, so that when cooling occurs we do not have any residual stresses. And these processes allow metals to be deformed in compression without breaking the metal. And on the right we see different processes involved. This is rolling. This is very commonly used to get sections, where a larger piece of the metal is pulled through rollers to get the desired shape and section. The pulling through can also be done without rollers, using a die in the case of drawing wires and thin products. This drawing can be aided by a ram pushing the material through instead of just pulling through a die, and this is called extrusion. Then there is the possibility of applying force to create a certain section. For example, in forging, force is used to give the material a certain section or shape. Deep drawing, again the material is clamped and there is a negative piece which gives the shape pushed against the metal to give the required shape, say to form a cup shaped element and so on. Bending is used to give again the desired shape, similar to stretch forming and shearing. Shearing is used to cut materials into the lengths and the shapes required. For steel structural members, the usual method of forming is cold rolling. The usual method of forming is hot rolling with cylindrical or shaped rollers at temperatures of 1000 degrees or more. Again, we use the higher temperatures so that we can have recrystallization occurring and there are no residual stresses. After the rolling, the members are allowed to cool naturally, ending up with an annealed microstructure. And we discussed annealing already in a lot of detail when we were looking at the strain hardening and so on, and we find that after annealing the material will not have residual stresses and will have a stable microstructure. Now, the cooling of the material to ambient temperature also involves the formation of an oxide film on the surface. When the material is hot, an oxide film forms on the surface and this remains on the metal, and this generally helps the metal in terms of corrosion. The oxide can prevent further corrosion and this stays on the surface. One disadvantage of hot forming is contraction. As all materials contract, reduce in dimensions on cooling, hot forming also gives rise to this issue. So, the dimensions that we will get in the cool state should be anticipated in hot forming, and in the hot form state probably larger dimensions are needed in some aspects, so that the final element has the desired dimensions that we need. Metals and alloys can also be cold work. This again we have discussed in the previous lectures, the advantages of cold working and also the disadvantages. Here the metal is worked on at temperatures below that of recrystallization. There is not much change in the microstructure. Many metals and alloys can be cold worked, that is shaped at temperatures below that of crystallization, and this gives rise to strain hardening and increase in the tensile and the yield strengths. This, however, as we saw in the previous lectures, leads to a decrease in the ductility or the elongation, and this again we have seen before that this is caused by the dislocation movement, and the dislocations result in the piling up of dislocations, hindrances due to the grain boundaries and work hardening. The consequence is that we now have a metal with a higher yield strength. There are many cold working processes. Cold rolling, again when at room temperature, rolling is used to decrease the dimensions, and this results in sheets that are having higher yield strengths than the parent material. Wires are also drawn at room temperature. This is called cold drawing. High strength wires are obtained. Fibers that are used in concrete are made with such processes. Cold extrusion is also possible, similar to what we had in hot working. Extrusion can also be done in cold working, again leading to strain hardening and increase in the strengths. There is, however, a limit to cold working. Beyond a certain limit, the ductility of the material is completely exhausted and the material fractures in the process of cold working. So, we should understand what the stress strain behavior is in order to know how much to push the material into the strain hardening extremes. There is a change in the microstructure of the materials also during cold working, depending on the process involved. Suppose we have cold working due to rolling, and a polycrystalline material before rolling would have a microstructure with equiax grains, that is grains with similar dimensions in all directions. However, if rolling is done, we have now elongated crystals, crystals that are elongated in the direction of the rolling. So, you see the crystals are all elongated this way, and this microstructure now remains after the cold working. The material changes from being isotropic to now anisotropic. Different pieces of metals also have to be joined before the application, and there are several processes involved in joining of metals. Adhesive bonding is where a substance like a glue is used to bond different pieces. This is being used increasingly, but not very common. Diffusion bonding is a solid state process that we discussed earlier, where two pieces of metal are pushed together, temperature is applied, diffusion across the element boundaries occurs, and we have a case of an alloy forming near the bonded region, and this sticks the elements together. A common process of joining metals is welding, where the material is locally heated to above the melting temperature, and now the material fuses. Additional material can also be added, say a metal can be used to finish off the welding. The joint is then allowed to cool naturally. This should be done such that there is complete continuity between the parts. This is often not achieved, and if it is not properly achieved, then there could be defects which could lead to fracture and failure at the joint. The joining material, suppose an additional material is used, should have properties that are better than the parent material. Otherwise, this would be the weak link and failure would occur again at the joint. Brazing and soldering are similar to welding, but what happens is now the temperature is lower than the melting temperature of the parent metal. So, this involves the joining of parts by means of a thin film of filler material. The temperature is lower than that of the parent material, however, it is high enough for the filler material to melt. This now flows into the joint, it wets the joint through capillary action. Remember, we had talked about wetting when we discussed surface properties. So, the filler material should be such that it melts at a reasonably higher temperature. The filler material should be such that when it is in the molten state, it wets the joint by capillary action, then solidifies with properties comparable to that of the parent metal. In soldering, the filler material melts at much lower temperatures than in brazing filler materials, less than 450 degrees Celsius. Now, we had said that one of the problems of the using of metals in applications is that the metals tend to revert to their original state that they are found in nature through oxidation. Oxidation and corrosion are very big problems in civil engineering, because this can hamper the life of the structure made out of metal. Corrosion can now be divided into two parts: dry oxidation and wet corrosion. All metals, as we discussed earlier, occur in nature in the oxidized state except for gold and silver. And when we have a metal exposed to the atmosphere, a thin layer of oxide first forms on the metal surface. Further oxidization depends on what can diffuse through this oxide layer. For further oxidation to occur, either metal ions should diffuse out through this first layer of oxide, or oxygen ions should diffuse in for oxidation to continue. The rate of oxidation therefore depends on the thickness and the structure of the oxide layer. If it is thicker, then oxidation will be slower, and if the structure is such that it is very impermeable, it does not let anything in or out, then again we find that the rate of oxidation is lower. When the oxide that forms has less volume than the metal itself, then it shrinks and cracks. This exposes the fresh metal to oxygen, and further oxidation can continue to occur. Sometimes we have the oxide occupying more volume, that is, it has more volume than the metal from which it formed, and there what will happen is it will delaminate, it will try to stretch, wrinkle and fall off, again exposing fresh metal by creating a new surface. In some metals, however, the volume change is not that much, the volume does not change that much. This leads to thin adherent layers that stick on the original metal. This prevents further oxidation. Such oxide layers form in aluminum, chromium and nickel, and this is the reason why chromium and nickel are used to make stainless steel. In the presence of water and moisture, this corrosion process gets even worse. The loss of metal becomes more significant when we have moisture and water. Metal ions dissolve in water, leading to steady corrosion, and this occurs through an electrochemical process that we will discuss further in the following slides. Let us consider a divalent metal M, that is with a valency of 2. So, what happens when you have an electrolyte and there is enough oxygen available and water available? We will have the metal first releasing electrons. This is the oxidation reaction or the anodic reaction. Then we have hydroxyl ions forming from the oxygen and hydrogen. This is the reduction reaction. So, first we have an oxidation or anodic reaction producing electrons. Secondly, there is a reduction or cathodic reaction consuming these free electrons. These two are called half cell reactions. So, this occurs whenever a metal is exposed to both oxygen and moisture. In some cases, the metal ions react with the electrolyte and deposit near the cathode. Iron is one which has corrosion that way, and this involves two reactions. At the anode, we have iron releasing the electrons, this can result in a cation with a valency of 2 or 3. Water splits up into hydrogen and the hydroxyl ions, hydrogen is released, and at the cathode we have the iron ions reacting with the hydroxyl ions giving iron hydroxide FeOH2 or FeOH3, and this is what you would notice sometimes as an orange slimy substance that is found near iron that is submerged in water. You will see some orange liquid near the surface of the iron. So, that is iron hydroxide. This is later converted to iron oxide and water as the water evaporates and the material dries. You have rust forming on the surface, that is iron oxide. This is a diagram showing the different reactions that we have discussed. We have an anodic reaction that is now causing the loss of material. Iron ions now dissolve in the electrolyte, there is a release of electrons, and at the cathode we have hydroxyl ions being produced. Oxygen and water are required for this cathodic reaction. This now results in depletion of material at the anode. The material starts to be removed at the anode and deposited elsewhere, say near the cathode. Corrosion can also occur when two dissimilar metals are in electrical contact. Electrical contact not necessarily means that they are touching each other, but they could be an electrolyte which is connecting them. Say here we have a piece of iron and a piece of copper in a bath which could be water with some impurities or some salt solution. So, what happens now is that the copper electrode becomes a cathode, the iron electrode becomes an anode. So, the iron piece starts losing material, iron ions now go into solution, and we have a cell formed between the iron and the copper pieces, and this is called a galvanic cell. And this is very important because in many applications we have dissimilar metals in contact or in the same application, and this could mean that one of them will preferentially corrode because of this galvanic cell. So, when pairs of metals are immersed in an electrolyte, wherever there is some sort of a solution, one will become the anode and the other will become the cathode, and the anode will corrode. We look at the example of metals in seawater, and we can make a table which shows which will corrode more with respect to another. This is called the galvanic series. So, in seawater we will find that magnesium out of the different materials listed here will corrode fastest, followed by zinc, aluminum, mild steel, cast iron, lead, tin, brass, copper, nickel, stainless steel and monel. We find that higher up we are in this table, more anodic the material gets, that is, it corrodes faster. And when we have two metals in contact or within an electrolyte, what is higher up will corrode faster than the other. It will protect the other one from corroding and corrode. Later on we will see that this is used to create sacrificial anodes when we want to protect steel, say mild steel, from corroding. If we have a piece of magnesium with it, then the magnesium or zinc would corrode rather than the mild steel. We also find that in an alloy, say in brass, when we have more zinc, the corrosion potential is more than in brass which has less zinc. More impurities distort the material and strains the lattice, causing a higher possibility of corrosion. At the bottom of the table we have materials which we know do not corrode very easily, like copper, nickel and stainless steel. So, as I said, this table means that when we have materials in contact, say mild steel and brass, the mild steel would corrode faster than brass. However, if we had something of stainless steel and brass, then the brass would preferentially corrode because it is higher up in the series or in the table. The process of wet corrosion also can tell us how we can design materials or design components such that corrosion is prevented. We see that when the composition of an electrolyte changes, that is the concentration of dissolved oxygen changes in the electrolyte, this can cause preferential corrosion. The part that is getting less oxygen will corrode more or become anodic, say in this case of a riveted joint. If we have the joint such that water can go in and there is water stagnation in this area, obviously the part that is inside away from the surface will get less oxygen. So, this part becomes the anode and this starts losing material, metal starts dissolving from the interior in the anodic part and we have now a cell that is set up. Unfortunately, we will not be able to see this happening because this is hidden from vision as it is protected from getting oxygen. However, this is what is corroding. So, if we have a design such that water is going in, stagnating, then we will see that this part will have corrosion occurring. So, this if this is put in an incline, for example, in on a roof and water goes in here, then this can lead to lot of corrosion. So, it would be rather that this is inclined this way, that water runs off and does not stagnate here. So, this dependence on the amount of oxygen in the electrolyte gives rise to significant issues when we want to protect materials against corrosion. In a riveted or bolted junction that we saw, areas that are inaccessible for inspection as well as oxygen will become anodic and corrode, since the electrolyte there is poorer in dissolved oxygen. This also we see in pitting corrosion. The bottom of the pit is further away from the surface and therefore, it gets less oxygen. This region is poorer in oxygen and therefore, becomes anodic. The consequence is now that pit becomes deeper and deeper, leading to premature failure, which again happens because in an inspection we see only the top surface, we do not see the depth of the pit, and the depth of the pit could reduce the section and cause a defect to be formed, which can become a crack later. Similarly, we find in sheet piling with steel in stagnant water, the surface layers are richer in oxygen, whereas the lower layers are oxygen deficient. So, what we find is at the top we need not see any corrosion occurring, but just below the surface, not very much below, but just below the surface where you have lesser oxygen, the layer of steel becomes anodic and starts to corrode locally. So, again requiring inspection and proper design such that areas which could get less oxygen are protected against corrosion and inspected periodically. Now, corrosion becomes worse when stress is applied, and this is normally the case in most civil engineering applications. You would have a metal having some sort of load or stress. This gives rise to what is called stress corrosion and consequently stress corrosion cracking. This results from the combined action of tensile stresses and a corrosive environment. Most materials become susceptible to corrosion under stress. small cracks form and these propagate, eventually leading to brittle failure. Sometimes a stress or a load may not be necessary, just the residual stresses due to previous mechanical actions like strain hardening, cold working or thermal actions, thermal fatigue, cycling of temperature can provide enough stress to cause corrosion. And this is one reason we have higher corrosion possibility in strain hardened materials, because you have grains now which have higher energy, they have surfaces which have higher energy and therefore can corrode faster. In brass, this is how stress corrosion would look like. You see the grains, the small grains, this is a polycrystalline material, and at the surface now we have surface of the grains, we have areas of higher energy, these are surface defects that we had discussed before, and when this material has some stress along with a corrosive environment, the crack starts to go along the grains through the grain boundaries and causing crack propagation and ultimately failure. So, this occurs due to the combination of the stress which is accentuated at the defects along with the penetration of corrosive material in the crack, leading to further crack propagation and failure. There are several strategies or needs for minimizing damage. Some are easy to apply, some are more in the design phase and others in the operation and maintenance phases. First of all, we should try to reduce the operating temperature. This decreases the rate of corrosion. This is not always possible. We might not be able to change the operating temperature, but if we can insulate, we can decrease the temperature at which the material is in, then we will reduce the rate of corrosion. We can also choose the right material. Slight changes in composition can improve corrosion resistance. For example, elements that produce protective oxides, films like we had discussed before, chromium, nickel, titanium can be incorporated in a metal to increase the corrosion resistance. So, this affects the choice of the material to be used in a certain application. We can look at design modifications, avoid heterogeneity, prevent contact between dissimilar metals, for example, steel and copper. So, this again comes from the elimination of galvanic cells between the two dissimilar materials, which will cause corrosion of the more anodic material. For example, if we have steel and copper in contact, steel will corrode. So, this is something that we can keep in mind during design to avoid dissimilar materials from being in contact. Secondly, we should avoid any stagnation of liquid, water in the application. By minimizing sharp corners, depressions, connections where water can stagnate and not dry off. If we keep a material dry, then the possibility of corrosion is also less. Other than this, we can take active precautions to reduce or eliminate corrosion. This is in the form of cathodic protection, protective coatings and the use of corrosion inhibitors. So, this we will look at in more detail. Cathodic protection is based on the reversal of the direction of the metal oxidation reaction. That is, the metal that we want to protect, the metal that we want to not corrode, we force it to become the cathode. We ensure that this metal does not become an anode. We know that corrosion is an electrochemical process. So, a common way to provide cathodic protection is to use an electric current to supply extra electrons. The metal piece that is to be protected is connected to the negative terminal of a battery, and a scrap metal, a scrap anodic metal is connected to the positive terminal. So, we use this scrap anode to sacrifice it and therefore protect the metal that we want to keep for a long time. This scrap anode has to be periodically replaced as it will be consumed over a period of time. So, we need now a battery or a power source plus a sacrificial anode for this system to work. We can further help the process by covering the protected metal with plastic or some coating, so that the cathodic area is reduced, and this has to be done in periodic locations, so that the complete element is protected. Suppose we have a pipe under the ground and we want to ensure that this metallic pipe does not corrode. So, we force this pipe to be a cathode through the use of a battery. The battery now is connected to an anode which is losing electrons. This is some scrap metal that we can continue to replace. This is nearer the surface, we will excavate and keep changing this anode. Now, we have to have several batteries along this pipe at a periodic locations to ensure that the complete pipe is protected. Additionally, we coat the pipe with an adequate coating, say a plastic coating, to ensure that the exposed area is reduced. So, this is how cathodic protection is done. Alternatively, what we can have is go to our galvanic table and choose a metal which is more anodic and make that as the sacrificial anode, and in this case we do not have a battery, we do not need the battery to provide the electrons. What we do is we ensure that there is contact between a metal that is more anodic than the metal that we want to protect. So, this metal that we want to protect will become cathodic, the anodic material will corrode and sacrifice itself. So, often what is done is, to protect steel we will have pieces of zinc or magnesium placed in contact at again a periodical distance, so that this zinc or magnesium will corrode and protect the cathodic material from corroding. So, when you have large areas we have to have many of these sacrificial anodes, and these anodes have to be replaced often. So, this is an alternative to having a battery that is giving the cathodic protection. Sometimes we have that even in reinforced concrete, to protect the reinforcement we embed these sacrificial anodes in the cover, so that they can be sacrificed and protect the reinforcement, which if it corrodes can lead to failure. Sacrificial anodes are widely used in marine environment, especially in ships, offshore platforms. It is systematic to put pieces of zinc or magnesium in contact with the steel, so that they can corrode, and they are periodically replaced and protect the steel in the application that we want. A second way of active protection is the use of protective coatings. There are two types of coatings: a coating that could be cathodic, that is it provides galvanic protection using a material that is more anodic. So, we know that this coating will sacrifice itself and protect the main material, or it could be a coating which simply becomes an impermeable layer that prevents contact between the external fluid and the metal. So, in the first case we use anodic metal coatings to protect, say, steel. We have lot of applications, we have zinc coated steel in use. The zinc coating protects the steel even after the coating may be scratched, because the zinc will corrode rather than the steel corroding. Chromium plating is also used many times, but that will not protect the steel much, because chromium is more cathodic than steel, and what will happen is when corrosion starts, a small pit appears in the coating, and underneath it you can have the steel corroding, and unfortunately you will not see the corrosion occurring because the chromium plating is at the top. you will find that eventually corrosion has been occurring and you have a loss of material. So, chromium plating, though it is used a lot, is not a good way to provide cathodic protection. Zinc coatings have been used for a long time and they are very efficient in giving cathodic protection. You have also non-cathodic coatings such as epoxies, enamels, bitumen, Teflon, paints, lacquers, which are used to protect metals. So, these basically give an impermeable layer on the metal. They limit the diffusion of oxygen water through the layer, this protective layer, to the steel that we want to protect. However, a major problem is what are called pinholes or holidays. Holidays meaning that there is a discontinuity in the layer. Small areas of the coating could be accidentally exposed due to a scratch or somebody cutting something accidentally, resulting in this scratch or exposure of the base metal. This results in the formation of a corrosion cell with a high anode to cathode area ratio. There is a large area that is not exposed to oxygen, which can become anode, and a small exposed area which can become a cathode. So, there is a high anode cathode ratio and there you could have a corrosion cell forming. One way to make this coating better is to have particles such as zinc in the paint that we use, so that if at all there is a pinhole or a holiday, the zinc will corrode rather than the base steel corroding. Passive oxide layers can also protect. Remember, when we talked about oxide layers, we said that some oxide layers do not have much volume change. They stick to the surface of the metal and will not allow oxygen to go through or the metal to diffuse out. This can be enhanced further by a process called anodizing, where we purposefully increase the thickness of the oxide layer. Or anodizing involves the application of a high corrosion potential, giving rise to a thicker than normal oxide layer, and this oxide layer now protects the anodized metal from further corrosion in application. So, this becomes part of the processing itself. We purposely increase the oxidation layer by anodizing, and this prevents further anodizing, further corrosion from occurring. A final way of looking at corrosion protection is through inhibitors, where we add special chemicals to the electrolyte, not to the metal, to the electrolyte, to decrease the diffusion of ions to the metal electrolyte interface. The inhibitor may act by forming an adsorbed layer on either the cathode or anode, such as in chromate salts, or like in the case of sodium sulphate, we can have less dissolved oxygen in the electrolyte, and as we know, we need oxygen, we need water for corrosion to occur. So, if we cut the supply of oxygen, we have less corrosion. The use of inhibitors you can imagine is limited, because we cannot go anywhere and put this inhibitor in all applications. Inhibitors are used a lot in closed applications, where you have, say, a tank that is recycling some liquid, or in any other closed space where we have solution always in contact with the metal. One application is in reinforced concrete. Corrosion inhibitors are added to the concrete such that they can get into the pore solution and prevent corrosion of the reinforcement. Some limitations of the use of inhibitors are such that some limitations in the use of inhibitors are that the chemicals are toxic, some of them at least, and therefore, we cannot have them be in contact with people. Secondly, if you have an insufficient dosage, if the dosage is not enough for the exact type of corrosion that is occurring, the corrosion can be enhanced due to inadequate coating, and also we will believe that the corrosion is going to be inhibited and it will not. So, these are tricky aspects related to the use of inhibitors, and therefore, there are limitations on where these inhibitors can be used. So, to conclude this part, we have looked at how metals are formed. We went through what is hot working and cold working, and then we went on to look at something that is very important, that is corrosion and oxidation. This often prevents metals from being used in some applications, increases the maintenance cost, and can also lead to failure. So, failure can happen not only because of the loads and stresses applied, but also due to corrosion due to the environment that the application is in. We will continue in the next lecture. We will look at different types of metals that are used, starting with iron and steel and going on to other metals. Thank you.